guys, welcome back to TechDose, and in this video we will look at the find the power of k size subarrays, which is from Leetcode number 3254. Let's now look at the problem statement. In this problem you are given an array of integer nums of length n and a positive integer k. The power of an array is defined as its maximum element if all its elements are consecutive and sorted in ascending order. Otherwise we need to return -1. You need to find the power of all the subarrays of nums of size k and return an integer array results of size n minus k plus 1, where results at I is the power of the array from the ith index to I plus k minus 1th index. Now let's look at an example for better understanding. Let's say that our given array is 1, 2, 3, 4, 3, 4, 5. In this case we have 7 elements, so n equals to 7. Let's say that our k value equals to 3. That means we want to find the maximum in all the windows of size 3 in such a way that all the elements must be strictly increasing within this window size, and all the elements must be equals to the past element plus 1 within the window. So if I consider, let's say, the first window 1, 2, 3, then we will always start comparison from the second element in the window and see that the previous element must be 1 less than the current element. The previous element must be 1 less than the current element, right? So this should be true for all the elements within the window except for the first item, okay? Because if you look at the previous item of the first item, it will be outside of the window. So these are the constraints which are mentioned in the question, and if these constraints are not followed, then we have to take -1. So if we have n equals to 7 elements, k equals to 3, then my number of sliding windows will be n minus k plus 1. This is already mentioned in the problem, right? So if I have 7 items, window size is 3, then we will have 5 windows starting at 0, 1, 2, 3, 4. Okay, after this we cannot start from 5, which is a window size 3, right? 4 will be the last window from 4 to 6. Now in all these windows we have to see that the constraint is followed. If the constraint is followed, then we have to take the maximum item and return it. So in the first window, are the items strictly increasing and each item is having one element gap, that means one value gap? Yes, this is true. So 1, 2, 3 is strictly increasing and they have one element gap, like 2 is 1 greater than 1 and 3 is 1 greater than 2. So this is following our constraint, so the maximum item 3 will be recorded. In the second window, if you go to the second window, we will be removing this 1 and adding this 4. Is it strictly increasing? Yes. And are these elements we are differing by a +1 value? Yes. So what is the maximum item? 4. So we will be recording it. Again we will be going to the next window. In this case I will be removing this 2 and I will have 3, 4, 3. In this case this is not strictly increasing, it is increasing decreasing curve. So this is not valid and I will write -1. If I go to the next window, I have 4, 3, 4. This is also not valid, so -1. When I go to the next value 3, 4, 5, then this is valid. Because in this case we have 3 items, all of them are strictly increasing, and so we will record a 5 value here, which is the maximum of this window. Now if you had noted the previous example 4, 3, 4, then in this case, even though this is increasing decreasing, but you can say that I will remove this 4 and then it becomes strictly increasing. But the constraint says that all the elements must be strictly increasing within the window. There should not be even a single item which is not following this thing, right? So we should be careful that all the k items are included. We should not exclude some items and say that rest of the items are following the constraints, right? So that is not allowed. Therefore the result array will be returned as an answer which will be of size n minus k plus 1. I hope the problem statement is clear. If you solve it by the brute force technique, in which you will see a window and find out the maximum and check if all the values are strictly increasing, then for every window you have to repeat for all the possible items. So how many windows you can have? N minus k plus 1, and then you will be repeating all these operations k number of times, and k can go to, let's say, a value n by 2, or even it can go to a value n. So in that case n minus n by 2 times of n by 2 will be equals to order of n square. You can just check it out, right? It will be n square by 4, so you can ignore the 4 value. So your brute force technique of checking each and every item in every window again and again will be n square. So this is the simplest possible approach, but then we have to apply some observation and find out the most optimal solution. In our case, we need to maintain the ascending order and maintain that every current item is greater than the previous item by one value. Okay, so if let's say that our given set of items are 1, 2, 3, 4 and so on, and our k value is equals to 3, right? Then our first requirement, as I said, is to maintain the strictly increasing order, and we already know that we can do all this kind of order maintenance by using two data structure, which is monotonic stack as well as deque. Deque can do all the things that monotonic stack can do, and it can do even more operations, right? So deque has more power as compared to the stack, but both of these can manage the items in strictly increasing, strictly decreasing, non-decreasing and non-increasing. Okay, so maintaining order can be done since by both of the data structure, but then we have another constraint in mind. That's how do you implement the sliding window. Let's say that my first window is 1, 2, 3. So I can take a monotonic stack and I can store 1, 2, 3 as strictly increasing into the monotonic stack, and in the monotonic stack I will have a top pointer here. Okay, now if you implement the same thing with the deque, then I can have 1, 2, 3 as the items, and this can be considered as the back of the queue and this can be considered as the front of the queue, or you can take front on the left or back on the right, whatever way you want. So in this case, if I want to include the next item 4, then the monotonic stack will be appending 4 here, right? And the top will be revised. But then is it the sliding window? Yes, I mean we have to include this 4, but how do you remove this one? So removing this one would require that you remove the last item of the stack. So you know that from a stack you can only insert and remove from only the top pointer, not from the last side, not from the other side, right? But in a deque, you can simply insert this 4 on one side and you can remove from the back, right? So due to this operation, the sliding windows are implemented using deque. So if you want to maintain ordering, along with that you want to implement sliding window, then we should always choose deque over monotonic stack, right? So in this problem, since the problem requires you to manage a sliding window along with maintaining ordering as well, so we will not go with the monotonic stack. Instead, we will be going with the deque approach. So now I hope that the choice of data structure is clear. So let's now look at the dry run using deque and the sliding window technique. Now in this case, I have taken an array of size 7 and my sliding window is of size 3. That means I will have n minus k plus 1 number of windows, and the number of windows will start from 0 and end at 4. So how many windows do I have? 7 minus 3 plus 1, which will be 5. So 5 windows. Therefore my result array will be of size 5. Now I will use an iterator and I will start iterating right from the beginning. Now what I do is I will be assuming front to be the left hand side and back to be the right hand side. Now initially the deque do not have any item, so both of them will be like pointing to nothing. Now when 1 comes, then I will insert it into the deque, but instead of inserting this values, I will be storing the index, because the index will actually tell us if I have inserted till some index number I, then I will know that if this 0 is outside of the window. If I store the value, then I can never know at what index it was at, but if I store the index, then I can also get the value as well as remember if this value has gone outside of the sliding window, right? If I write here 1 instead of a 0, then if I had included this 2, 3, 4 on the sidelines, then don't you think with the k value 3 I should remove this one? But how do you know that we should remove this one or not? Is it inside the sliding window, right? Because there could have been some insert delete operations in the middle as well. So you can just see the index here, it is 3, the sliding window size is 3, and you can check the index of this one, which is 0. So 0, since it is outside of the sliding window size, because start is at 1 if the end is at 3, right? So that is how you know that exactly I have to remove it. But with value it is not possible, hence I will be storing the index, right? So I hope this point is clear as well. So now I will be iterating for each and every item one by one, and I will be showing you the simple dry run. So I will be storing the index number 0. Every time we have to check if the I pointer is going to at least a value k minus 1. That means when the I gets to at least index 2, then only we get our first window, right? Before that we don't have a valid window. So until I reach to index 2, I will keep on inserting, and I will only insert if the values are actually increasing order, right? So index 0 will be inserted and index 1 will only be inserted if the top of the deque, that means the back of the deque, is actually 1 less than the current item, and that is true, so I will be inserting it. Okay, and the same goes for the next item as well. The index 2 will only get inserted if this index 1 is having one less value than the current item, so that we can maintain the strictly increasing order, right? So in this case, the back will be pointing here and the front will be as it is, right? Now the I pointer is pointing to k minus 1. So that means we have seen our first valid window. And since we are here, we will see the deque size. The deque size must exactly be equals to k. If it is not equal, then that means we do not have all the items in the order as per the constraint, right? As I explained, 454 can have 2 items increasing and 1 decreasing. So if you remove this, then there will be 2 items increasing, but that does not form a valid window. Okay, a valid window will have all the items included and strictly increasing and differing by a value 1. So deque size will be checked. If the size is equals to k, then the maximum value will be given by the back and just record it. So I will not record the index, but I will record whatever is the value at the given index, right? So 3 will get recorded. Okay. Now since we have formed our first valid window, then if you want to slide, then I have to include the right side element and I have to remove the left side element. So you can do whichever operation you feel like first. So I have done removing the left side element first. So I'll remove this element if this is outside of the sliding window, because the current item index is equals to 3. So if this index is outside of this I minus k plus 1, that means to the left of index 1, then that means it should be removed. And yes, it will be removed. So my front will be updated to index 1. After this removal, I will be including this 4, and I will only include this if the previously included item, that means the back of the deque, is actually having one value less than the current item. And that is true. 3 is one value less than 4. So I will include the index of 4, that means 3. And so the back pointer will be updated. So find out the deque size. It is equals to 3, which is equals to k. So what is the max value? It will be given by the back of the deque. So that value is 4. So I'll be recording 4 here. So this is equivalent to saying 4 was the maximum of this window from 1 to 3. Now I want to slide this window. So I want to remove this index number 1. So see, index number 1 is at the front. Remove it and you update the front value, right? Now you need to include this index number 4. But this index can only be included if the back of the deque is actually one value less than the current item. So if you want to maintain that, then this third index cannot be included, and I will pop it out. Again, check the previous back. This one is the new updated back, right? So this is 2. Again, at index 2, this value is 3. Is this 3 one less than the current 3? No, it is equal, right? So I will be popping it off. After popping everything out, your entire deque is empty. And once it is empty, you will be inserting the index of this 3, 4 into the deque. And this will be your new front and your back, right? And now you will be recording your answer. Now since the deque size is not equals to k size, that means you do not have k number of items in the window. This means that this window must not have been valid. If it would have been valid, like if it would have been 3, 4, 5, then the deque size must have been 3. If it is less than 3, that means it is not valid, and so I have to record a value -1. Okay. Now I will be again doing another sliding. So currently my window was from index 2 to 4. If I do another sliding, I should remove this index 2 and include this index 5. So check the front. Front is not saying index 2. Okay, so no need to remove that. It is already within the window size, right? Which is I minus k plus 1. Now try to include this index 5. Can we include this? You see this? The back of the deque is index 4. The value is 3. The current value is 4. So there is a 1 diff plus 1 diff. So definitely I can append this index 5 and the back will get updated. Now you find the size of the deque. It is 2. It is not 3. Therefore record a value -1 for this as well. Now my current sliding window is from index 3 to index 5. Now what we want to do is we want to remove this index 3 and include this index 6. Now the front of the deque is actually within the bounds, which is, this is your I pointer, right? The index 6. So 6 minus 3 plus 1, that is 4. So this is within the bound. So it is fine. I don't need to remove anything. Can I include this index 6? So check out. The back of the deque is having one less value than this value 5. So it is 4. So definitely I can include this 6 on top of it. And then we are done. We have implemented our sliding window. After doing this, find the size of the deque. If the size of the deque is k, that means it is valid, and the back of the deque will give you the answer. That means the maximum value in the current window. So index 6 will give you that answer, which is 5. So 5 will get recorded. And after this we are done because the iterator is going out of bound. So whatever is recorded in the result is our answer, and this array has to be returned. So I hope this technique is crystal clear. In this case we have done exactly one iteration for each of the item, and each item having seen will be pushed exactly one time into the deque and will be popped one time. So you can see an item exactly 2 times or not more than that. Okay, so that is why the time complexity will be order of n, and the space complexity due to deque is order of n, because you might end up pushing all the items in the deque if everything was strictly increasing. Let us now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. The code here is exactly the same, where we are given the nums array and the value k. I'll be finding the number of items, take the result array and take the deque integer type. So the deque will be storing all the indices, right? So I'll be using an iterator going from the first item till the last item in the array. And then first of all, I will be removing all the elements from the front of the deque. So let's say here you have a front and back and you have a bunch of items. So I'll be removing all the front items from the left hand side if it is outside of the sliding window, right? If the index is less than equals to I minus k, I will keep popping it out. After this, we will be including the ith item from the array to the back of the deque, and this is only possible if the back of the deque is having one less value than the current ith item, and if that is not true, then the back will have to be popped out, right? Unless the deque is empty, or otherwise the item x that we are seeing is actually one less than the current item that I am seeing in the array. That means if the current item is x plus 1, then the back of the queue should be pointing to an index which has a value x, right? So if that is not true, then I will keep on popping out the items. So this is removal from the back, right? And after everything is done, then we know that we are maintaining a correct window according to the constraint, and so I will just push the index I to the back of the deque as I had explained in the dry run. Now if the array index I is greater than equals to k minus 1, that means we will be seeing a valid window, and in case of a valid window, if the deque size is k, that means the entire window is valid, and so return the back item, which will be the maximum item since it is strictly increasing, right? Otherwise we will record -1 for that. And for all the sliding windows, we are recording it in the result array, so finally return it as an answer. So I hope this is clear. Now this problem is also solvable by binary search, but instead deque was more optimal and easier approach. I hope the solution is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video to keep us motivated to put more free content. See you guys in the next video. Thank you.